and explain what we're doing today. So the purpose of today is to talk through revision, because one of the things that we need to practice, as well as going over scientific information, it's really important that we keep practicing what revision looks like before we do tests or quizzes. Now, the test in inverted commas that we've got for you this week is entirely a multiple choice quiz on Google Forms. So there's nothing that's going to catch you out. What it's going to let you do is test your memory to see how well you're able to remember the things that I'm just going to go over for you now. It's practice, because you get better at revising by practicing it. And so that's quite an important thing to do. So there's not a huge amount of work to do after this. What you need to do is use the slides I'm showing you, which you've got in your Google Classrooms, to do some revision. That's the real work. And then the Google form you need to do after you've done some revision to see how that revision went. Okay, so let's get going. Let's start with a question. So that thing on that slide there is about Christmas tree lights. And in the 1970s, when I was little, and yes, I am that old, if one light bulb went, they all went out, and I used to have to watch my dad changing every single light bulb. And this is obviously about series and parallel circuits. So here's a question. Let's see what you remember about current in a series circuit. Let's see how your Battenberg cake is going today. Fantastic. And we're off with right answers. We're going pretty swift, mostly with right answers. That's really good. About half of you have voted now. Most people have got it right. Not everyone, but most people. That's brilliant. Now, obviously, if you don't get it right, that doesn't matter. It just means it's something that you need to go away and revise. If you do get it right, then that clearly is something that you don't need to revise anymore because you knew it already. And the answer there was stays the same the whole way round. Series, same. Current, series, same. Okay, series of them. That's how we start a Battenberg cake, with current. Cake, current, series, same. And then we can do the 4 windows like that. Okay, I'll talk about that a little bit later on. Okay, so maybe if we've looked at that, what about parallel circuits then? So what can you remember about how things work in parallel circuits? Now, I've probably deliberately confused you now. Oh, good. Actually, the answers that are coming in already are pretty good. Everyone's either got it right or said that they don't know because they've clicked this isn't the answer. No, really it isn't. Don't click it, and it isn't the answer, I can assure you. This one's a little bit more divided, although still with the majority of people getting it correct. I'm going to leave it for a little bit longer because that's only 30 seconds. I've just stopped talking to give people a minute of thinking time. Right, fantastic. I'm going to go with that because most people have voted now, and more than half of you got it right, which is the potential difference is the same in every branch of a parallel circuit. If we think about, we can either do it with a Battenberg cake and we can draw out the crosses and do cake, current, series, same as a one corner and then do the rest, or we could have a look at this tree, and obviously the potential difference needs to be the same for every light bulb, and that only works in a parallel circuit if the voltage is the same down each one. So that's quite important there. So what about these? Now, this is one of the first things that you need to revise, is you need to know your circuit symbols, and in particular you need to know these ones. So again, if you're revising at home, so now the series and parallel, current and potential difference, you need to find one of these slides. It's got a beautiful diagram across, looks like a noughts and crosses box with all of that on it. You need to know that. It doesn't matter if you remember it by the Battenberg cake method. It doesn't matter if you remember it by memorizing what that looks like or remembering the words. You need to know that in series circuits, current is the same the whole way round and potential difference splits up. In a parallel circuit, current splits up and potential difference is the same the whole way around. You must learn those 2 sentences. That's important. Okay, that's one of the things you need to revise. And then the next thing need to have a look at is you need to be able to identify different circuit symbols. So off you go. Tell me what that one is. What is the middle symbol in the top row? Start you off with an easy one. Middle symbol in the top row. That is this symbol here. I'll go round and round and round it like that. If I don't know how that works for you. Most people have got that right. That's fantastic. Middle symbol, top row. There we go. Most people have voted. I'll give you a little bit longer because there's a few more people voting. That's only 30 seconds. You've done very well. Right, I'm going to end that one because we're going to move on. That was a bulb. Excellent. So that circle with a cross in it is a bulb. So there are some more complicated ones on here. Like over there, that's a variable resistor, a volume control we use those for. And over here, I've got a thermistor. And remember, I said I remembered thermistors because it looks like an ice hockey stick and their resistance changes when the temperature changes. You need to learn those. The only way to learn those is to write them out, to draw them, to look at with their names next to them, look at them, remember them, try and cover them, and either cover the name and see if you can say what it is, or see if you can draw them out. If you had a list of names, draw the symbol next to it. You need to do one of those two things. You'll need to do it more than once to be able to remember them. It's important you try and remember the more complicated ones, these last 3 or 4, as well as the top row, which is the real basic ones. The top row you absolutely have to know, but it's really quite important that you try and learn some of the more complicated ones because those are the ones that often pop up in tests or exams. Okay, so let's try another one of those. So I said the top row is really important. So let's have another one from the top row. So now the right-hand one, this one right over here. Okay, the one that I'm moving the cursor over now. I want to know what that one is. Fantastic. And we're off with lots of right answers again already. Brilliant. Doing very well. Superb.
Hello, sir. I should say I'm very quiet because we've got no questions today.
Oh, superb. Well, that's a good thing. And I'm going to end this now. And absolutely everyone that picked one there, and it was most people have voted, everybody got that correct, that was a battery. So superb and very well done. Fantastic. So first thing, bit of your revision then. In series, current is the same. In series, potential difference splits up. In parallel, current splits up. In parallel, potential difference is the same. That's the first thing you have to go away and revise. And the second thing are those circuit symbols there. And then we get into a bit of real physics here. So we need to be able to do things like have a look at this sort of question and be able to say what the current is going to be. So if the current there is 2 amps, what is the current further round our circuit going to be? Okay. And we could have a poll on that. You could just quickly vote on telling me whether you know that. So if the current is up there, what's the current in any of those other places? And fantastic. So far, everybody has got that correct. So we're getting the idea. Now, if you know that in series current is the same. And if you know that, you can work out all the other things because everything has to be opposites. So if in series current is the same, that means potential difference has to split up because that's the opposite. In parallel, current has to be the opposite of series. So it's the same in series, it has to split up in parallel. Brilliant, well done. And you've all got that correct. That's another 100%er, so I can move on quite quickly. Fantastic. Now in a parallel circuit, I'm not going to put a quiz up for this one because a poll up for this one because you've quite clearly got it. So here's the current and half of it goes down each one. So if we had 4 at the top, we'd have 2 there and we'd have 2 there because in parallel current splits up. Okay, so we're going to move on from that one. Now, if all of the bulbs are identical, now in any question you get given about bulbs and voltage and resistance and things like that, just assume the bulbs are identical unless they tell you they're not, because it's what they expect you to do. So if we've got 6 volts up there for our potential difference, in series, potential difference splits up. So if we have 6 there, we will have 2, 2, and 2. It splits up nicely across them. Okay, so make sure that you have a read through these slides. I'm just going to go through, and there's lots of questions here for you to test yourselves on those. So this is the bit that's important. In a series circuit, current is the same, potential difference splits up. In parallel, current splits up, potential difference is the same. So that's your first bit of revision, series and parallel circuits and some circuit circuit symbols. And there was a challenge question there, but you won't have anything that difficult in your quiz. So I'm not going to put it there. The quiz is just about remembering some basic things. Now, we've got this guy, Georg Simon Ohm. I haven't spelt it wrong. I didn't miss an E off the end. Someone last week told me that I'd spelt his name wrong. I haven't. His name was actually Georg. And he is the person who came up with this idea of resistance. So anything that tries to stop a current running past. And remember, current was the flow of negative electrons. And Miss quite rightly told us last time that the reason it's I, it was intensity of current, intensité du courant. He did it it was done in French. It was Mr. Ampere, but that's why we've got I. Anyway, Ohm's law is this equation here. Okay, so V equals IR, or resistance equals potential difference over current. It's best to remember it as the triangle, but you need to be able to remember this. Certainly in your quiz, you're going to get asked to work out either a resistance or a current or a potential difference, given the other two. And without knowing this equation, you can't do that. So that's something you have to go away and revise. It's probably a good idea to know units as well. If you don't know resistance is measured in ohms and potential differences in volts, you're going to find it really difficult to do the calculation. So I would have a look at that. Formula triangles. So if you're not sure how to use it, you need to practice. The idea that when you want to work something out, you put your finger over the one that you want to work out. Whoops. Go back, and that leaves you with the sum that you have to do. So if you're trying to work out I, that tells you to divide V by R. If you put your finger over R, it would tell you to divide V by I, and so on. Okay, so that will help you. Now, we've got some graphs that we looked at, and some people drew some graphs or found it a little bit difficult. But actually, the one that I wanted to talk about with these three, where did it go? I definitely have them in here somewhere. Aha, there we go. Right. So far in your revision, you make sure that you know what a series and a parallel circuit is, really important. You make sure that you learn those circuit symbols. You learn the rules for current and potential difference in series and parallel. You learn that equation. Okay. Again, we're going to try and do all of that at once, even though we're going to post your revision quiz straight away. It'll be there by the end of today, but I wouldn't go and do it straight away. Give yourself some time. The quiz is going to take you about 20 minutes to do. Maybe leave it till enrichment week. You can, and actually spend some time trying to revise these things and do it a tiny piece at a time. Don't sit down and go, right, I'm doing my science revision 2 hours and I'm going to try and learn everything, because your brain won't let you do that. What would be best is if you said, right, I'm going to learn those circuit symbols now, and you draw them all out and you write down the names and you cover the names and you see if you can say them, and then 5 minutes, and then you go away. You do something else, and after 2 hours you come back and you try it again, and you do that a few times, and then you do the same with the equation. And over a few days, you just, by dotting little bits of revision here and there and doing lots of little bits, you will find it much easier to remember things than sitting down and going, right, this is when I do science revision. I do an hour and a half on Sunday afternoon and that's it, finished. Because that doesn't work as well as lots of little 5-minute slots dotted around. But you've got to have planned out what you need to do. So you need to write down, learn circuit symbols, learn two statements, learn equation, learn these graphs. What you need to be able to do with these graphs is you need to be able to identify what object you're looking at based on being given a graph. So a resistor is directly proportional. So that means that if you double the potential difference, you double the current, and you get this lovely straight line going up like that. A bulb curves at the ends. You get this lovely S shape. Because the bulb gets hot, it changes the resistance, and so the pattern changes. And because diodes only let current flow in one direction, they have a flat line because nothing happens, and then they're directly proportional in the direction that they allow. If you were given one of those images, you would need to be able to say which one it was. You don't have to explain why it's that shape, but you would need to be able to identify them. So there's another thing to revise. Again, the easiest way to do them is to write them down with their names next to them, cover the names, and be able to say that one's a resistor, that one's a bulb, and that one's a diode, and then come back to it another time. Again, it takes 5 minutes. Do it 3 or 4 times for 5 minutes, spread out over a few days. Much easier to remember than trying to do it all at once. Okay, all at once. Then there are some of these calculations in here for you to practice if you weren't sure. So V equals IR and some of those calculations. So that's pretty much all that's going to be in it to do with electricity. So you don't need to worry about anything else. Oh, you do actually. You can tell I wrote that. You do need to be able to work out resistance in series, certainly, so that you add them up. So to work out this resistance, it's 2 plus 4 means it's 6. You don't have to be able to work out resistance in parallel, but what you do need to know is the total resistance in parallel is always less than the smallest number that you've got here. Okay, it's always less than what you've got here. So you don't, it's going to be a smaller number than these two, okay, because of the way that it works out. So as long as you know that you add those up and that this number is always going to be smaller than one of those numbers, then you'll be fine, okay? That one you have to be able to work out. That one you have to just know it's definitely not going to be 6 or 4. It will be smaller, and then you'll be fine, okay? Brilliant.
I've had a
Hello.
request. Hello, I've had a request. Could you show the symbols again and name them, because they want to write them down, but I think that might take a little bit of time. But maybe
Yeah,
show them and quickly name them if you're able.
Okay, what I'm going to do, you're going to have to play this bit back. Okay, so we are currently 27 minutes and 30 seconds in on my recording. So I'm going to go through these and name them, but you won't be able to write them down this fast. Okay, but here we go. That one is an open or an off switch. That one is a closed or on switch. That one is a bulb. That one is a cell, and that one is a battery. So open switch, closed switch, bulb, cell, battery. Voltmeter, nice and easy, starts with a V. Resistor, fuse, it's very important, the one with the wire through the middle is a fuse. Ammeter, variable resistor, we find those in volume switches and dimmer switches. Thermistor, this changes its resistance as the temperature goes down or up. Light dependent resistor, this one changes its resistance depending on how much light is shining on it. Okay, so if you play that bit back maybe a couple of times, you'll be able to write them all down. It was a good question actually, because now you've got them all. Fantastic. So now the last bit, I'm going to spend longer on this than I have on revising the other ones, because this was new. We did lots and lots of circuits, and there were videos on circuits before there were webinars. Remember in those old days when we had videos instead of webinars?
Hello, sir. I'm going to interrupt you briefly just to answer this one for everyone. Yes, you are allowed a calculator in science tests. It's very important you have one. And my tip would be to actually do the calculation twice and remember to show any working, because sometimes you get a calculator error. And if you haven't shown your working, you're going to drop marks. So if you show your working and do it twice, you're guaranteed to be sorted. Sorry, sir.
No, don't apologise for that. That's a superb question. In all science tests, you're allowed a calculator. You're also always allowed a ruler and a pencil. And I would strongly recommend, obviously you won't need it for an online one, but always bring those to tests, because it makes everything much, much easier. And this rule is absolutely true. When you do any calculation in science, you must write your working down, and you must put all of the numbers into the calculator twice and check it. It only takes an extra minute, and it can save you so many marks. My year 11s that have just left were really in the habit of me refusing to mark answers if they didn't write their working down, because on some big GCSE questions, there can be 6 marks for a calculation, and you could get 5 of them with the number at the bottom still being wrong. If your calculation was all correct, but you put the numbers into your calculator incorrectly, you must write them down. It's essential. Right, forces. More importantly, the idea of resultant forces, working out in which direction a force is going to act if we've got 2 or more opposite forces. So here we had some, and we were talking about contact and non-contact forces. So for example, magnetic force was non-contact. You can feel two magnets pushing against each other or attracting without them touching. Gravity is a non-contact force. You don't have to be touching the ground for the earth to be pulling you down onto it. However, other ones were contact forces. Air resistance doesn't work if you're not in contact with air. Tension force doesn't work if you're not holding on to something and pulling it. So contact and non-contact. Have a little look at those. But then we went on to resultant forces, and we went on to this idea that there are equal and opposite forces. So when two objects push or pull on each other, they exert equal and opposite forces. I'm sitting on a chair right now, and the reason, even though gravity is trying really quite hard to pull me down onto the floor, and in fact through my ceiling and into the room below, I'm not falling down because the chair is exerting an equal and opposite force to gravity on me, and so I'm completely still. So that's how that works. But sometimes those forces, one of them does actually win. For example, here's a car, and we've got a driving force. That's the force from the engine turning the wheels, and that is pushing our car forwards in that direction. But as it goes forwards, two forces try to stop it, because as it goes forward, it hits air particles and they create air resistance, and they make it more difficult for it to go forwards. And also the wheels are rubbing against the road, and they create friction that's also trying to slow our car down. But if our car keeps speeding up, that means that the driving force is bigger than those other two forces pushing back against it. So let's imagine driving force was 50. Okay, now we can work out how much force makes our car go forwards. So we've got 50 going forwards, but air resistance was 30. So air resistance was 30 going that way, and we had 50 going that way. So our resultant force would be the 20 that was left that wasn't being cancelled out, going in this direction. That's what we call a resultant force. Let's look at some with some numbers actually on them. Here's a rocket. So rockets create thrust. That's what makes them go up into the air. And this rocket produces a thrust of 2,000 newtons. It has a weight, so that's how hard gravity is trying to pull it down, of 1,000 newtons. What is the resultant force on that rocket? Now, the tricky bit here is that I have to try and find the right pole, and I'm not sure if I'm going to be able to do it because I have so many here. Oh, I can. There you go. So what is the resultant force on that rocket? Let's see how you're feeling about that. Oh, we're 100% so far. This is going very well. Nearly half of you have voted, and it's all correct so far. Absolutely superb. You don't have a difficulty working out resultant forces, it would appear. Well, half of you don't, because half of you have voted. If it's because you're not sure, still vote, okay? Because that lets me know how people are doing that. At the moment, I think everyone knows this because everyone's getting it correct. Okay, superb. Right, and because you don't know what each person's putting, no one's should be worried now. So nearly everyone's voted. Right, I'm going to tell you the right answer, even though I haven't closed the poll. The right answer is 1,000 newtons. In fact, it's 1,000 newtons up. Okay, and the reason is, if we wrote numbers on here, we've got 2,000 up and we've got 1,000 down. Because they're opposites, we have to take one number off the other one. So we've got 2,000, take away 1,000, which leaves us 1,000 newtons. And we know it's up because that's the direction of the big force. It's always going to be in the direction of the bigger force. So what about if we tried something different? So that was really good. You worked that out. But what about if we had a rocket that produces a resultant force of 1,000? That's the same rocket we just talked about. It hits a wall, and that wall makes it stop. What size does the force from the wall have to be on the rocket to make it stop? Not make it bounce off. It doesn't bounce the other way. It doesn't go through. It stops. What size would that force have to be to do that? Good. Superb. This is going very well indeed. Quite a lot of you have got it already, so you don't need to revise this. Really quite impressed with that. I mean, you might want to revise it anyway. So it's mostly correct. We've got most answers are correct right now, but not all of them. So I'm going to explain why. I'm going to explain why. The answer to that one is 1,000 again. Okay. Now the reason is, if we've got a rocket going along with 1,000, a resultant force of 1,000, that's making it accelerate in that direction. But it has to decelerate down to 0. So we have to make the force become 0 so that there is no acceleration of that rocket at all anymore. So if we've got 1,000 that way, we have to have 1,000 that way to make it stop. If it still had some force in this direction, it would actually go through the wall. If the wall hit it with a force that was harder than 1,000, it would make the rocket bounce off and go in the opposite direction because there would be a resultant that way. So for it to just stop and fall down, there has to be no force, and that's going to need 1,000 in the opposite direction. So this was one of your tasks, and I'm aware that some people found it a little bit tricky. I'm going to see if I can draw on it now to make it a little bit better. Okay, so I'm going to get my annotate tools. Excellent. I'm going to do draw, and I'm going to pick arrows. Fantastic. Let's see if I can do it. So I've got a car of weight 5,000 newtons. So I'm going to put on an arrow here, and I'm going to make this arrow B for 5,000 newtons. And it's got a driving force of 2,000. So that means that my driving force has to be less than half the size of that 5,000 there, because they've got to be proportional. Remember my arrows. Now it experiences friction force from the ground of 500. So I've now got 500 going that way. That's quite small, and that's friction force from the ground actually. So let me draw the friction force from the ground over here, and that can be air resistance up there for 500. So let's put those numbers on. So this one up here is 300 newtons, and this one, this one over here, let's see if I can move that box to somewhere suitable. This one was 2,000 newtons. Let me just move the box. Let's see if we can put that somewhere where you can see it. Fantastic. And then down here, I know this is going slowly, but hopefully this is going to help. So down here, we've got 500 newtons, and then here's the big one down there. So let's put my text down there. Now I've got 5,000 newtons. Brilliant. So what are the horizontal and vertical resultant forces acting on the car? So let's do the ones straight backwards and forwards, because that's the easy one to do. I've got 2,000 going to the right of the screen that way. And I've got 300 plus 500 because they're both going in the same way, so we can add them up. So I've got 800 going that way. I've got 800 going that way. I've got 2,000 going that way. I take my 800 away from 2,000, and I've got 1,200 left going forward. So brilliant, my car is going to be accelerating forwards. But now I've got 5,000 newtons down onto the ground. Now this is where people go wrong. Lots of people say, well, there's only one arrow there. I'm going to draw 5,000 down into the ground. Brilliant. Well, if that was happening, if there was 5,000 down, remember I talked about my chair? That would be me going through the chair, through the floor, through the ceiling, and onto the ground below me. If there was 5,000 down on that car and nothing else, the car would be going through the tarmac, through all the pipes underneath, and being crushed down into the ground. It'd be sinking. Because remember, we said every force has an equal and opposite reaction. So this car is being pulled onto the tarmac with 5,000 newtons. That means if it's not sinking, the tarmac is pushing back up with another 5,000 newtons. Because it's not moving up and down, remember our rocket, if we don't want it to move up and down, the resultant must be 0. So it must be being pushed back up with 5,000 so that the resultant is 0, because it stops moving up and down. It's not moving up and down, there's 0. Okay. Now, you might need to watch that little clip back again to be able to make sense of this. I'm not going to explain it again, but you can pause this and play it again and maybe link it in with the thing about the chair. This is a more advanced idea. So if you're still really struggling with this, don't worry about it. But you've got to remember that if something isn't moving, its resultant has got to be zero. So you've got to work out where the other force is coming from. Okay, you don't let it. I've got to stop drawing now. There we go. Stop drawing and it'll let me move on. Fantastic. And then, oh, it's not got rid of the arrows. They're just staying on my screen. That's annoying. The other thing that you need to do. Hello, miss.
I've got the question. So the gravity doesn't stop the car. So I don't know if you want to talk about gravity and weight.
Yeah. Okay. So gravity is the force between any two objects, and the big object that we worry about is the Earth. The Earth exerts a force called gravity on everything on the Earth. Okay, my phone here has got gravity exerting a force on it, and I've got a pencil here, gravity is exerting a force on it. But the amount of force is affected by the mass of that object. I am more massive than my phone. And so my weight, which is the force due to gravity, my weight is higher than the weight of my phone because there is more of me than there is of my phone. But gravity pulls things down and it creates a force called weight. So as gravity attracts things, it creates a force called weight. And the amount of weight is dependent on the mass of that object. So the more of the object there is, the more the force of gravity is. So gravity creates the weight, which is pulling something down. Oops, that's gone away. I was trying to take those there we go. I wanted rid of those because they were annoying me. I hope that answers that question. I'm not sure if that was the question I was asked, but I hope that answers the question. So weight is the mass of an object times gravitational force. And gravitational force on Earth we take to be the number 10. Okay, so if I have a mass of 70 kilograms, that means my weight, which is my force due to gravity, is 700 newtons, because we always measure force in newtons. Okay. Now, one of the most troublesome contact forces is air resistance, because it slows things down. And when you slow things down, it makes them less efficient. So if we're talking about cars, in fact, let's talk about electric cars, because electric cars are the future. They're probably what you're all going to be driving when you get older. And for electric cars to work, they have to be really efficient. They have to find ways of using as little energy as possible to move forward to make their batteries last longer. And to do that, they have to slide through the air instead of trying to shove the air out of the way. And we do that by making them streamlined. We make streamlined objects. And it's really important that you understand that that is a shape that allows things to present as little surface as possible to the air. Sometimes we try to increase friction. Friction is important when we don't want to slip. So these two vehicles here, this big wheel bike and this Jeep, are designed to travel on mud. And mud is slippery, and so to prevent them from slipping, we try and increase friction by making their tyres bigger and flatter so that they are able to increase their friction force. That's everything you have to revise. So what have I gone through? Circuit symbols. Try and learn the names of the circuit symbols. Series and parallel. What does current do? What does potential difference do? What is current? Flow of electrons. What is potential difference? The push the electrons have got. What's resistance? Go back and have a look at Georg's slide. What was his equation for his law? V equals IR, or the triangle. Could you work some of those out? There are some to try. Could you recognize those diagrams of current and potential difference graphs for those three different, the resistor, the bulb, and the diode? Can you name contact and non-contact forces? Are you able to draw a free body diagram? That's an object, a diagram with arrows on it to show forces. And can you work out a resultant force? Do you know the rule that says everything exerts an equal and opposite force on something else? So if something has got an arrow drawn on it, but it's not moving, there is another force somewhere that brings it to zero. And then do you know what the word streamlined means? If you've covered all of those things, you're going to find the quiz really easy. I'm going to say again, we are not using the quiz to put you into sets, to catch you out. It's for you to test, does my version of revision work for me? Because if it doesn't, you need to practice it some more. Revision is important. I'm going to talk about sets again because I keep getting asked. I'm getting emails from parents. We are obviously going to put year 8 going into year 9 into sets. A letter is going to go out to everyone, but so many of year 8, we go on and on about how fantastic you all are at science. It's really true. We don't just say that to every year group. This current year group is really good. So we're going to have 2 classes where we start looking at triple science material on each side of the year, so far more people. But the other thing that we're going to do is, because you've had so much time out of school, we're going to move people around to make sure that they're in the right set all the way through year 9. So people will move up and down after tests just to make sure that everyone's in the right place to get them the best GCSE grade we can. So it's not something you should be worrying about right now. I know lots of you are, and lots of your parents, because I get emails about them. It's something that we're going to do when we come back in September, and we're going to keep looking at every time we do something in science. Each learning cycle, we'll look at it again. So there's plenty of chance for people to be in a different place as the year goes on. What you need to be concentrating on now is enjoying engagement week and then really enjoying your summer holidays. Now that we're allowed to spend a little bit more time out doing things and seeing friends, that's what you should be concentrating on, and not worrying about what we're going to do back at school next year. So have a fantastic time, and I'll see you in enrichment week.
Sarah, I did have a question.
No.
And it
Yep.
made me giggle because I was just getting images. It said if a plane was flying